we learned about electrolytes in Chem 1A, and whether an electrolyte is weak or strong or a non-electrolyte depends on the extent of its dissociation. So a strong electrolyte dissociates completely into its ions. And soluble ionic compounds are like that. They will dissociate completely, sodium and hydroxide. The sodium ions and the hydroxide ions all split up in the aqueous solution. A weak electrolyte only dissociates partially. And really the only weak electrolytes we talked about in Chem 1A were weak acids. So the strength of an acid depends on its equilibrium. So here we have an acid, and we'll see this abbreviation a lot, HA. What does A stand for? There's no element A. It's just something, right? So this is some substance, right? Usually it's going to be something like like Cl minus or NO3 minus or something like that. But this is just the main part of the acid, and that's the hydrogen that it's going to give off. So here, this hydrogen ion can be donated to the water. So here we have an acid and a base, and then we form the conjugate acid and the conjugate base. So A minus is the conjugate base of this acid. So a strong acid will completely ionize, which means that it would go completely in the forward direction. All of the molecules will ionize, whereas a weak acid only ionizes partially. Okay? So there are 6 strong acids. Memorize them. There's only 6. So, how do you know if it's a strong acid or a weak acid? Well, there's 6 strong ones. If it's not one of the 6 strong ones, it's weak. Okay? So we've got hydrochloric, hydrobromic, hydroiodic. These are what I call the halogen sisters, chlorine, bromine, and iodine. And why is fluorine not in there? Well, fluorine is the littlest sister, right? Things get bigger as they go down. Fluorine's at the top. She's the little sister. She's not strong. She's weak. Okay? So these 3 guys, and then nitric acid, perchloric acid, and sulfuric acid. And so, these are very common acids, and I'm sure you can figure out how to remember which ones are strong. A monoprotic acid, mono is a prefix meaning one, protic referring to the proton, one proton acid. It has one ionizable hydrogen. So here we have the chemical formulas, and the H's are in red. And so these guys have one ionizable hydrogen. And these guys also. This one, H2SO4, has 2 ionizable hydrogens. So we refer to that as a diprotic acid. It's got 2 protons. A triprotic acid has 3. Can anybody think of an example of a triprotic acid? H3 something. I'm going to assume that someone's saying it. PO4. H3PO4? So this is a triprotic acid. That ionizable hydrogen is always written first. And so when we write acetic acid, it's HC2H3O2. This is the ionizable hydrogen. There's 3 other hydrogens in here, but those do not ever get donated. So in general chem, we always write that ionizable hydrogen first. So a strong acid, like HCl, HCl dissolves in the water. It ionizes completely. It's donating its hydrogen ions to water molecules, forming hydronium ions. It's got chloride ions. And we don't see any intact hydrogen chloride molecules, right? So here it is with pictures instead of letters. So here's our molecule. When these dissolve, all of them separate. We don't see any of these guys hanging around in the solution. So when we write this equation, we use the single arrow, which indicates complete ionization. Do you think that means that there's not even one HCl molecule present? Is anything that absolute? Nothing is. There might be a couple in there, out of bajillions, right? Is that of any consequence? Does it matter at all? No, it doesn't. So we say this completely ionized. So if we have a 1 molar HCl solution, all of the HCl ionizes, forming hydronium ions and chloride ions. So all of the HCl becomes H3O+. If we start out with 1 mole per liter of this, we end up with 1 mole per liter of hydrogen ions. That make sense? Here's a weak acid, HF, the halogen baby sister. So HF is a weak acid. When we write its equation for dissolving in water, it will donate a proton to the water molecule, and it will form H3O+ and F-, but this is an equilibrium. It only happens partially, does not go to completion. So when we look at the pictures over here, HF dissolves in water, and some of them will donate their protons, but a bunch of them do not. And that's what weak acids do. So if we have a solution that's 1 molar HF solution, and we're interested in the concentration of the ions that it produces, we cannot say that H3O+ is also 1 molar, because a lot of it stays HF. So without more information, all that we can say is that the hydronium ion concentration is much less than 1 molar, because a bunch of it stays as HF. Any questions? So what makes some acids strong and some acids weak? Well, it depends on the interaction, the attraction between the conjugate base and the hydrogen ion relative to the attractions of those ions to water. So here, HA, if the attraction between H and A is very strong, then it's not likely to give up many of its hydrogen ions to the water. And so then this is a weak acid because it does not ionize completely. So what's a little confusing about that is when you have a strong acid, there's a weak attraction. When you have a weak acid, there's a strong attraction. I hate it when we've got two things that we have to match up. It's like, is it strong, strong, weak, weak, or is it the opposite? So don't try to just match those up and memorize them by rote. A strong electrolyte conducts electricity strongly, right, because it makes lots of ions. A strong acid makes lots of ions. It will go to completion. Well, why does it give up all of its hydrogen ions? Because it wasn't that attached to them in the first place. So, this is the parent that goes out a lot, right? And I guess you could say, well, they're a strong parent. They're really confident in themselves, right? So they go out a lot. They pass the kid off to the babysitter every chance they get. A weak acid is very attached to its hydrogen ion, and so it'll only give it up a little bit. There's lots of different analogies we could make. Find one that works for you so that you can remember it. But one thing that we will be talking about later is the stronger the acid, the weaker the conjugate base. Well, how do we measure that equilibrium? We do it with an equilibrium constant. The equilibrium constant here is called Ka. It's the acid ionization constant. So it's an equilibrium constant for the ionization of an acid. So here we have our generic acid, HA, reacting with water, forms hydronium ions, and this conjugate base. So this is writing it using H3O+, and this is what it looks like when we write it with H+. So the H+ equation gets a little simpler because we've taken H2O out of both sides. So we'll use this method a lot just because it makes the chemical equations simpler. It means exactly the same thing. Because when I look at this and I see H plus aqueous, I don't think, oh, there's individual protons floating all over the place. There's little babies running around on the sidewalk. No. All of those hydrogen ions are being held by a water molecule. I understand that, so I don't need to write it all out. So this can be a little confusing, but these two are meaning exactly the same thing. Well, how do we calculate an equilibrium constant for these guys? Let's look at the top one first. We take the products and divide by the reactants. Right? So we've got H3O plus times A minus divided by HA. Why don't we have H2O in there? It's a liquid. The liquid concentration doesn't change. Liquids and solids do not show up in the equilibrium constant expression. So for this one, then we can say, well, it's H plus times A minus over HA. If we have a small equilibrium constant, that means that the numerator concentrations are small relative to the denominator, right? The product concentrations are small relative to the reactant concentrations. The reaction does not go very far. Right? A large K is a stronger acid. If we have an actual strong acid, we can't even write Ka for it because this denominator is essentially 0. Strong acid is understood to ionize completely. So these are some acid ionization constants for some monoprotic acids. These are all weak acids. It never fails in a class. I get a lot of students who don't memorize the things I tell them to memorize. And then there's usually one student, and I'm not saying that anyone in here has become that student, but it just happens every semester, so I just can't, I have to talk about it. It's not uncommon for me to get a question like, do we need to memorize table 17.5? Who would even ask that, right? No, we don't memorize this table. If we need that information, we look it up in the table, right? So we're not going to memorize any Kas, okay? Here we've got names of the acids, their formulas, their structural formulas, so we can show how things are connected. And like here, benzoic acid, there's a bunch of other hydrogens here, but those are not highlighted in red. Those do not get donated, they stay. This is the one that gets donated. We have the ionization reactions for them, and here is Ka, the equilibrium constant. And we'll see that all of these numbers are small. These two guys down here are extra small, 10 to the minus 10, but all of these are small numbers. And we'll talk about what pKa means in a few minutes. Any questions? On an exam, you would either be given a table like this or the Ka value would be provided in the question. On homework, they may not give it to you. They want you to go look it up. I recommend looking it up in the textbook because if you look it up online, these are not absolute numbers, right? These are not exact numbers. They're measurements. And you may find different sources that disagree a little bit. So if you use Ka from a different source and you plug it into Mastering Chemistry, your answer might be different enough that it says you're wrong. So just use these guys. let's talk about the magnitude of the acid ionization constant. So here we have illustrations of 3 different generic weak acids. We're calling them HA, HB, and HC. And these are representing the ionization at room temperature, and they're asking us which one has the largest Ka. Does a large Ka mean that more ionizes or less ionizes? More ionizes. Because Ka is the product concentrations divided by the reactants. So for K to be larger, we need more product, we need more ions. So which one of these has more ions in it? B. And here, it can be a little hard to distinguish. Oh, well, there's one without the hydrogen. It's easiest to just look for the little white ones. There's 4 white ones here, and 2 there, and only 1 here. Consider these 2 acids and their Ka values. Which acid is stronger? Neither of them are strong, but one is stronger than the other. A is stronger because the Ka is larger. Watch out for these negative exponents. They can play tricks on you. Right? The smaller negative exponent is bigger. If they were positive, it would be the reverse. So this equilibrium constant, Ka value, is larger because more of it ionizes. There's more product than there are for the other one.